Okay, so here we're just going to go over the method of standard additions that you'll be using on the AA lab, the one for the atomic absorption spectroscopy. That's where you're measuring the concentration of calcium ions in some fruit juice. There's already on Canvas a video of Dr. Sharp going over it, but I just wanted to go over an explanation as well because sometimes it's helpful to see more than one explanation of something. So, just to introduce some notation here and a bit about what's happening, we have some sample solution, which in this particular lab, the AA one, it would be your fruit juice, and it has a concentration of some kind of solute, in the specific case, calcium ions. And the concentration is CS. That's the little subscript S, and that's what you don't know, but it's what you want to know. So, just like how you did other solutions when you were doing Beer's Law or the ISE experiment, you made calibration standards, but first you had to make some standard solution from a stock solution. So you do that same thing here. You'll make some standard solution of the calcium ions or whatever the solute is, and it'll have concentration C STD, C standard. And so I've drawn that in there as red. Then what you'll do, instead of making a series of several solutions of varying concentrations out of this standard, you'll make a series of solutions that also include the sample solution of unknown concentration. So here's what that might look like. So if we consider the case of making 5, now it doesn't have to be 5. You could do maybe 4. You could do more than 5. I don't remember how many you do for this lab, but I think it might be more than 5. But in any case, make a series of solutions. Now you make these solutions in a specific way. We're doing the method of standard additions, but we're doing a specific method of it called method of constant volume. And the constant volume there refers to how much volume of the sample solution you add. In this case, it's a constant volume of it. So to each container, you will add the exact same volume, in this case, Vs, of the sample solution. So you can see here, I've drawn it here in black. The same height is in each one of the containers for the unknown solution, the sample solution that we don't know the concentration of. Then to each of these solutions, we add some of the calibration standard, of the standard solution that we made, and we know the concentration of this because we made it. Now, it's important that we note that we don't add any of it to this first container. We add 0 of the standard solution to this one, but we add some to the rest of them. And importantly, we have to make sure that we note exactly how much of that volume we add to each one. And you can see we add increasing amounts as we go to the right. And so we note that in red as the volume of the standard solution that we've added to each one. And then finally, we top each one off with solvent, with some volume of solvent shown as green, in order to make sure that they are at the same total volume. Okay, so they might be 50 milliliter flasks, they might be 100 milliliter flasks, whatever the container is, whatever that total volume is, they finish off at that same volume. And so each one has the same volume, but they will have differing concentrations of the solute, the calcium ions in the case of this particular lab. Okay, so different concentrations, same volume. They have the different concentration because of the different amounts of the standard solution that we added. Okay, that's where that different concentration will be coming from. But now we might well ask ourselves, well, what is that total concentration in each one of these? The total concentration in each one of these is going to simply be the amount that was in the sample that we added, right? The amount in each one of these containers that came from adding this portion of the sample solution to each one, and the amount that came from adding the standard. So in this case, we added no standard, so that would be 0. And in each one of the rest of them, it would be an increasing amount. And then we divide that by the total volume. The total volume is easy enough. That's just VT, and it's the same for each one. The amount in each one of the containers up here that came from the sample is also the same, because the sample solution has this single concentration, CS, and we added the same volume, VS, to each one. But the amount that came from the standard will be different, because although the standard has the one concentration, we added different amounts of it, and so that's where the difference will be coming from. And then finally, we divide by the total volume, VT. If we rearrange this slightly, we have that the total concentration, CT, in any one of our containers will be equal to the concentration of the standard times the volume of standard added to that container divided by the total volume of the container plus the concentration of the solution, this is the quantity we want to know, times the volume of sample solution added to each one of these containers divided by the total volume. Okay? And that will be the total concentration of the solute that is in any one of those. And now we use Beer's law. So Beer's law comes in, and it's the same procedure as it was previously. Once again, we have the absorbance equals the absorptivity times the path length times the total concentration of the solute. Okay? So this is always just going to be the total concentration of the solute. But we know now that the total concentration of the solute is given by this expression here, which relates it to the concentration in the sample solution and the concentration in the standard solution that we made. So we can substitute that expression in for total concentration, which we've done here, just copying it down. And then rearrange it slightly. Send this absorptivity and path length onto each one of those terms, distribute it through the parentheses. To get this, just simply rewriting it. And now we can make a plot. So just like how we plotted absorbance versus concentration before when we had calibration standards, we again plot absorbance versus something. Now you have some options here in terms of what you plot it versus, but your options are going to be plotting it against something that includes the volume of the standard added to each one of those solutions. Okay? Each one of these. So let's look first at an example. I'll cover up this portion here. Let's look first at an example of plotting the absorbance versus the concentration of the standard solution times the volume of the standard solution added divided by the total volume. Just this portion here in parentheses, this whole thing. So if we plot it against this, right, it's important to know that we would be making these dots, right? These dots are our measurements. So we measured the absorbance, that tells us how high they go. And we know the concentration of the standard we made, the volume that we added to each container, and the total volume that we diluted it to. So we can plot these dots. And then, just like before, we make a calibration line. Sorry, we make a linear regression line, just like this. And we get an equation that will be a straight line, y equals mx plus b, where x would be the horizontal axis value, y is the vertical axis value. From this regression equation, we obtain a slope, and it will have some value, right? Something like 1.23 or something like that, an actual number. But we'll call it m hat, just because we don't have actual data that we're working with right here. And the y-intercept will be b hat. Okay? Now, in doing this method, of standard additions, it's normal that you extrapolate the regression line past the 0 of the x-axis and over here to the x-intercept, where absorbance would equal 0. So we mark that as x-int, standing for x-intercept. If we solve our regression equation, the y equals mx plus b, for the x-intercept, we just set y equal to 0, solve for x. We obtain x-intercept equals minus, so negative value, the y-intercept divided by the slope of the line. And that'll be the value of the x-intercept that we would obtain from extrapolating this line down to here. So now we return to our expression of Beer's law, where we have that the x-intercept is the value of this quantity. And how do we know it's this quantity? Well, because that's what we plotted over here. It has to be the same quantity that you plotted in your figure. The x-intercept is the value of that, which gives a 0 absorbance, so A equals 0. So we want to find out, what is that? We need to write this equation. We need to write this equation with absorbance equals 0. If we do that, we just simply write 0 equals, and then the rest stays the same. But we mark int on this quantity because we're noting that it is the portion that corresponds to the x-intercept. And in fact, it is equal to the x-intercept, right? Because all we did was set the y value, the a, and that corresponds to the y value in the regression. We set those to 0 here. And so that means that this quantity in the parentheses, which was the horizontal axis value, needs to be the intercept. So that's the x-intercept. So solving for this guy here that contains our concentration in the sample solution, we solve this equation, making the substitution that this in parentheses is the x-intercept, we obtain this equation here, that the concentration in the solution, in the sample solution, times its volume, times the volume added to each container in our series, divided by their total volume, equals negative of the x-intercept. Where we note that, again, the x-intercept is equal to this, like we saw over here. Solving for this concentration, we obtain this expression here, that it will be equal to minus the x-intercept times the total volume divided by the volume of the sample solution added to each one of our series of solutions. Okay. And that's how you can obtain the concentration in the sample solution here. Now, I'd mentioned that you have some options here in terms of what you plot. You'll always want to plot absorbance, but you don't necessarily have to plot this specific thing. You have to at least plot the volume of standard added, since that's the only thing that changes in each one of these. Of course, the total concentration in each one of the solutions changes, but you don't know the total concentration because you don't know the concentration of the sample solution. But you do know how much volume of the standard solution you added to each one, and that's something that you can plot against. So two other options that you might plot are as follows, and they'll get the same results from each one. So one option might be that you would plot absorbance versus concentration of standard times volume of standard. So we just aren't plotting it against total volume as well. On the previous figure, we had that same thing, get them both here at the same time. We had that same thing, concentration of standard, volume of standard, but we're not dividing by total volume this time. So once again, the x-intercept will be whatever the y-intercept is that this line gives us divided by its slope. And of course, we'll have to put a negative sign out front of that as well. It's important to know that if you compare a figure with this is the horizontal value and this is the horizontal value, the intercept and slope will be different. And so the x-intercept will probably be different as well. But the procedure from there is much the same. Once again, we take our Beer's law expression and set the absorbance equal to 0. And we write that this is the horizontal axis value, C standard times V standard, from here. And so that will be equivalent to our x-intercept value, which again was the y-intercept by the slope and negative. So we solve again for the quantity which contains the unknown concentration, Cs. And the epsilon L divided by total volume, that all cancels out from each term because it's 0 on this side. So you get Cs times Vs equals minus x-intercept. So that the concentration in the sample solution will be negative x-intercept divided by volume of sample solution added. So that's if you plot it against this. Finally, if you plot it against only the volume of standard added, you would have this result. So again, you would have whatever this equation ends up being. It will likely have a different y-intercept and a different slope. But whatever the case, the x-intercept will always be the negative of that y-intercept divided by the slope. So again, we set the absorbance equal to 0 in our Beer's law equation, recognizing that now, since we're plotting it against V standard is the quantity that will be the x-intercept. Solving for the concentration of the sample solution, we again see that the absorptivity and path length cancel out from each term. The total volume cancels out from each term as well, so that we can solve for Cs times Vs and get minus C standard times x-intercept coming from V standard here. Therefore, solving for Cs, we get concentration of the sample equals minus concentration of the standard times the x-intercept divided by volume of the sample solution added to our series. So it's 3 different ways that you can plot the data in this method of standard additions. You can either plot it against the volume of the standard added, the volume of the standard added times the concentration of the standard, or you can plot it against, put them all 3 up here, the volume of standard times concentration of standard divided by total volume. But you see in all 3 methods, they include the volume of the standard added. And just make sure that you use the correct equation for evaluating the concentration of the sample solution that corresponds to the method of plotting that you used. Okay. Also worth noting that the specific units that you use for volume and concentration don't really matter when you're making these plots, as long as you are consistent, as long as for every concentration involved, you are using the same units, and for every volume involved, you are using the same units. Otherwise, it doesn't matter. You can use parts per million for concentration, or you can use milligrams per liter, milligrams per milliliter, or whatever. And you can use liters, milliliters, anything you like for the volumes. Again, as long as you're consistent between all of them.